Hi, everyone. I'm Marsha. I'm a lead for Google Developer Group Los Angeles. And I wanted to present Liza Goldberg, who will be talking to us about harnessing space technology. She's going to complete a live demonstration with Google Earth Engine during this talk, and it will guide you in understanding how Earth observation technology can increasingly create transparency around critical indicators of global change, enabling more informed policy decision-making to protect our planet. Take it away, Liza.
Thanks so much, Marsha. I'll start my video. Hi, everyone. Thank you so much for joining today. I'm really excited to share with you just a brief introduction of Google Earth Engine, a geospatial analysis platform that remote sensing scientists, environmental scientists around the world use to capture space technology and apply it towards monitoring some key aspects of global change. So to introduce Earth Engine, I'll begin with a brief PowerPoint, and then I'll move on to a series of live demonstrations. Hopefully you got the link to sign up for Earth Engine so that you can follow along on your own. And if not, then you can just follow along on my screen, and I'll point you to the sign up link afterwards. So I'll start with sharing my screen. Okay, so many of you may have seen images or GIFs like this one. This one shows a meandering river in the Amazon rainforest. You can see this pretty incredible time lapse starting from the 1980s all the way to the present day. And what you're seeing in this image is hundreds of thousands of pixels that we can get from satellite data from space. Many of you might be familiar with the hundreds of operational satellites run by a range of different space agencies around the world, NASA being one of them. And each of these different satellites provides a range of different data that we're able to use to capture various aspects of our changing planet. So things like precipitation, temperature, and the kind of true color Earth images that you saw from GIFs like the one we saw before. There are over 40 years of remotely sensed data available from this constellation of satellites and sensors. But before Google Earth Engine, there really wasn't any capacity to condense all of these data in a form that was actually accessible to scientists around the world. Scientists used to have to actually download each individual satellite image over one particular geographic area in order to be able to begin analysis on it. But this is where Google Earth Engine comes in. So Earth Engine, you can kind of think of as the back end of Google Earth. Many of you might be familiar with kind of satellite view on Google Maps, for instance, or the Google Earth platform itself. But Earth Engine is where we can store all of the satellite data that goes into providing those images for you. As of now, there are over 50 petabytes of Earth observation data, everything from kind of typical satellite imagery to weather data hosted on Earth Engine. And the key here is that Earth Engine really operates on Google computational infrastructure. So the main improvement that Earth Engine makes over kind of past models of remote sensing data is that with Earth Engine, you actually don't have to store any of these enormous satellite remotely sensed data sets on your personal laptop. All of it is stored by Google itself. And you're able to then access these data using a JavaScript API, just using a browser. And there's now actually really strong Python support as well. But this, on kind of an equity note, was a major advance over previous platforms too, because all of these data are actually available entirely for free. And all you need is actually just an internet connection to access this JavaScript API. So what Earth Engine was really able to do when it was first formed was really transform the capacity of scientists in low and middle income nations in particular to be able to do these kinds of environmental science analyses. What you're seeing here now is actually one of the first products that was created from Google Earth Engine. So you're seeing a pretty incredible image here, and it's incredible because there are no clouds. We know that typical remotely sensed data is very cloudy. There are a lot of different spectral effects that we have to account for here. And this kind of greenest pixel composite showing just the greenest pixel in each one of these areas in kind of a summertime composite has no clouds. And it's kind of a beautiful representation of kind of the initial launch of Earth Engine and what it was able to do in terms of enabling scientists to now do these analyses globally rather than locally. Once this first cloud-free composite was created, Google Earth Time-Lapse was created. And Time-Lapse basically took 30 years of the entire Landsat satellite record. So Landsat is one of the most commonly used satellites that we use in all forms of environmental analyses. And this was kind of the official launch of the historical data in Earth Engine, showing that we're able to do cumulative analyses over time. And here's just kind of a quick global representation of some of these changes in sea ice that you can see in the Arctic over time, showing kind of what it looks like, again, to create these global scale composites and time-lapse images that we can see. Moving on to the local scale, you can see I really like showing these time-lapse images, but these are really powerful visualizations because for the first time with Earth Engine, we're actually able to really not only quantify this change, but also visualize it. And when we are able to visualize these changes, like for instance, urbanization in China, then we're able to catalyze policy change and change public opinion as well. In this next visualization, you can see Amazon deforestation, and I link time-lapse itself at the bottom of this image where you can go and explore many different hotspots of key global changes around the world. All of these analyses, again, were kind of just driven by Earth Engine itself. So ultimately, to wrap up kind of this overview of what's possible in Earth Engine, we know we have now about 33 years of satellite data stored in Earth Engine, over 5 million Landsat and Sentinel scenes analyzed. So you can think of a scene as just kind of a small part of a single image. I mentioned Landsat was a very common satellite used, launched by NASA and USGS. Sentinel is the radar equivalent from the European Space Agency, and just many, many pixels. This is really global, local to global scale analyses. So the data catalog is really the core of what Earth Engine is able to provide. So I've mentioned a couple different forms of data, but at this point there are over 200 public data sets that you're able to use that range from things like MODIS data, which is basically daily weather data. We can look at terrain and land cover data, things like where are agricultural areas versus cities versus forests. And importantly, you can actually upload your own vectors and rasters. Basically, that's just Earth Engine terminology for spatial data as well as imagery. And you can think of the Earth Engine data catalog as being searchable, kind of like just a Google search for global scale data sets. And I'll show you how to actually access this in the Earth Engine JavaScript platform soon. Good, but generally we are able to access data over every pixel around the world, including in many territories where, for instance, journalists can access on the ground. So much of my work deals with things like conflict and displacement monitoring in territories where satellite data is actually the only way to be able to tell these changes that are happening on the ground. It is worth noting, because I do get the question a lot, that in some regions of China, for instance, and some in North Korea, it becomes a little bit more difficult to access some imagery because there are some privacy and access restrictions. I'll quickly just show a couple sort of beautiful examples of these visualizations that we're able to create using Earth Engine data. Here we see terrain data. So this is looking at things like mountains, where we can see kind of differences in elevation over time. These terrain data are really useful for building flood models, for instance. We see atmospheric data. This can help us a lot with understanding weather patterns. Sentinel-1 data is radar, as I mentioned, and it's really accurate for, or a better use than Landsat data for cloudy regions, for instance. And now moving on to kind of a really brief overview of what Earth Engine is able to accomplish programmatically in terms of which functions you're able to do. Here I just kind of quickly list them off. The satellite image is sort of the fundamental data structure within Earth Engine where you're going to be doing all of your computations. You can have a collection of these images showing kind of a stack of all of the data over time. The feature is kind of the fundamental spatial structure within Earth Engine. So you can think of a feature as kind of like a shape on the map, and a collection of features would just be a bunch of shapes that you're able to kind of capture your image over. Features are really useful, for instance, when you don't want a global scale image, but you just want to restrict an image to a particular region. Filter is how you can limit the scope of analyses temporally or spatially. So again, if you just want to look at satellite data within a certain time period or over a specific space. And I won't go over the rest of these today, with the exception of machine learning applications. Today we'll just be doing some really simple ones, but it is worth noting that the Python API is by far the best when it comes to the machine learning capacity within Earth Engine, and much of Earth Engine's data analyses can now be exported to TensorFlow if you're interested in doing more complex analyses. It's important to note that now with Earth Engine, you can do both on-the-fly computation if you're interested in kind of interactively visualizing the data, serving queries, and previewing the results of your analysis. So this is really useful when we do things like build apps within Earth Engine to allow policy stakeholders to see the results of the analyses that we're building. And now there's new capacity to do batch computation when, for instance, we need to export many, many images from Earth Engine to an external source. I'll go over this briefly again in a moment, but this is really where it all happens. This is the Earth Engine JavaScript code editor. And you can see it looks a little bit different than your typical coding interface, given that there's a map that automatically responds to your lines of code above. So on the left here, where it says your data, your scripts and example scripts, you can think of this as kind of like your file folder for Google Earth Engine. It's where you save all your documents. You're able to write code in this kind of middle area, use the output console to print information about your data sets, and then automatically map the results down here. In terms of how the Earth Engine code editor actually works, the code that you write in the code editor gets turned into an object representing the set of instructions that you give it, which is then sent to Google for processing. And this analysis that you requested, it then runs in parallel on many computers. This is just basic cloud computing. And what you get back in your browser is only what you request. So for instance, a statistic or a chart that you print to the console, or some small red, green, blue images that you're printing on your map. And this is all low bandwidth analyses, but it's basically as if you had access to a supercomputer. If you're more interested in how Earth Engine actually works, I really encourage you to check out this kind of iconic paper by Noel Gorelick that goes over sort of the back end of how Earth Engine operates in RSE. So now I'll finish off this slide deck today with some applications. So this is a relatively new Earth Engine application that was just released using Earth Engine in the backend. It's called Climate Engine. And Climate Engine allows users to basically interactively create maps of climate data and trends, but without actually writing or reading any code. So this is really important when we think about how to translate Google Earth Engine data to policymakers, for instance, because we know that many of our users are not going to be able to use the JavaScript API. And so using Earth Engine, you can actually process all the data. And then you can connect Earth Engine to App Engine, for instance, if you're interested in creating these more complex applications that run on Earth Engine analyses. This is another kind of app resulting from Earth Engine as a backend. This is what's called the EcoDash monitor in Vietnam. And basically what it's showing is cumulative anomalies indicating the trajectory of this project area in terms of forest health. So this is showing regions in red that are having a bit of a hard time recovering from forest disturbance, and regions in green that are doing relatively better. This is a project that I just took from my own work. I do a lot of work in Bangladesh on brick kiln monitoring, for instance, and this is just the simple classification running on Earth Engine machine learning algorithms that basically identifies brick kilns, which are primary sources of pollution across Bangladesh. And using this really simple app that we created for policymakers, users are able to click on specific points in the map and plot nitrogen dioxide and SO2 over time to see if the pollution levels are getting better or worse during different times of the year. And this is another example from my own work. This platform is really intended to enable corporate entities who we've partnered with to be able to better track their supply chains and regions of the world where their activities are really infringing on protected areas. And this is intended to help these users really see which areas of operation are in conflict with growing environmental and conservation regulations around the world. So what this shows is that Earth Engine can really also be used as a key means of creating transparency around environmental threats, whereas many supply chains around the world have previously remained kind of hidden from global eyes and not able to be regulated by global policymakers. What we're able to do with Earth Engine now is really kind of use these eyes from the sky to understand regions around the world that are at risk. So now moving on to the kind of more interesting part, which is actually the demonstrations within Earth Engine. So again, I'm really hoping that a lot of you are able to click that link and sign up with Earth Engine. I will note that Earth Engine now requires a Google Cloud account to be able to access, but if you intend to use it for academic or research use, you don't need to add a credit card. There's no charges. I will say, though, that Earth Engine is now a commercial entity for those who are interested in profiting off of these analyses. So I'll stop sharing my screen for right now and X this out. Before I keep going, I'll just ask if there are any questions on kind of the general idea of Earth Engine before I go on to the demo. Okay, if there are no questions, then we can just go ahead and move on to the demo portion. So I'll share my screen again. And the first thing that you're going to want to do is go to code.earthengine.google.com. And what you're seeing here is the JavaScript code editor. This will be the easiest place for you to get started with your Earth Engine analyses. If you're more comfortable in Python, the documentation for the Python API is now also relatively well developed. And so I encourage you to also try that out. But for now, we'll just start with JavaScript. And again, I'll just kind of repeat these different parts of the JavaScript API. Here we see on the left our kind of file folder with all of our codes. Here we can just, I'll show you a quick hello world. We type in this main part in the center and we press run and we see our results in the console. Down here is our primary map where we're going to see all of our results. Over to the left of console, you see your inspector where you're able to click on the map and see the latitude and longitude. Right now, since we haven't mapped anything, you don't see any map values, but when you actually do add a map, then you'll be able to see the value of that particular satellite image at that exact point location. Here to the left of the save button, you see a get link button. This is where you can get a shareable link to your Earth Engine code. And then while I won't be going into it today unless we have time, there is also a capacity to generate these Earth Engine apps right here, where basically all you need to do is just code your app within the main console here, and then you can make it publicly available up in this apps area. So the first thing that we'll do today is just do a really quick demonstration of how to map global forest extent, forest loss, and forest gain. This is really critical to understand sort of basic data structures within Earth Engine before we get to more complex analyses. So the first thing we need to do is actually bring in our satellite data set. So up here, we can search forest change. And this, again, is kind of like your Google search for data sets. And we want to select the second one here. Again, these rasters are just collections of satellite images. This Hansen Global Forest Change data set was actually one of the first global published papers on Earth Engine. And if we click on it, we can see some basic information about this data set. We can see it's available from 2000 to 2023. And over here next to the description, you can see these bands. So the bands you can kind of think of as just data categories that we can work with in our data set. So here we see we have data on tree canopy cover for the year 2000, where every pixel is going to represent, be assigned a number representing the percentage of that pixel's area that is covered with forest. We see a binary image showing forest loss, as well as a gain image, and we won't worry about these for right now. If you're more interested in the background of this paper, I encourage you to check out the actual paper, which was published in Science. We go to the bottom here and we press import. And now you can see it's automatically brought into our imports area. And now we need to actually name our data set. So let's just name this forest change. And this essentially just renames the variable here. So the first thing we want to do is map forest cover for the year 2000. So again, this is mostly JavaScript, but also has some kind of strange syntax with Earth Engine, so just bear with me for now. We're going to have to define a variable called forest. And we're going to take our forest change data set, and we're going to use the command select. Now, select just selects a particular band of data that we're interested in. So in this case, if we remember from the data set, the bands that we're interested in is our tree cover 2000 band. And that's actually all we need to do to just isolate these data. And now let's actually try adding this to the map. So to add something to the map, we use map.addLayer. And there are 3 different parameters that we put within this command. So we'll say forest is the layer that we want to add to the map. Then we can put open and closed brackets. And within these brackets, we can put what's called our visualization parameters. So this would be the minimum and maximum values that you want to visualize with, as well as the color palette that we want to use. So in this case, since we're visualizing tree cover from 0% cover to 100% cover, an appropriate palette of colors would be something like white, yellow, and green, where white will represent the lowest tree cover and green will represent pixels with the greatest tree cover. And we'll say our minimum value is 0 and our max is 100 because, again, this is a %. And then we'll just get out of our curly brackets and we can name this layer tree cover. I'll leave that up for a moment for those who are copying to finish. And now we can actually run this. So when we run our just simple 2 lines of code, we're suddenly able to get this global map. And as you can see, pixels that we would expect to have very little forest show up in white, whereas these really significant forested areas like the Amazon, for instance, show up in this kind of deeper green, with yellow pixels being sort of somewhere in the middle, maybe closer to 50% covered by trees as of the year 2000. But let's say we're interested not just in where the trees are, but also where forest loss and forest gains are. So let's say we want to map forest loss. Just to give some extra practice, it's really similar to our last line. Let's define a variable called loss. And here we'll say forest change.select loss, because this is the other band that we're interested in. And then this is going to give us a binary image with black and white pixels, depending on whether loss occurred in that pixel or not since the year 2000. But for visualization purposes, we're probably only interested in the pixels where loss occurred. So in this case, we can use this convenient command called self-mask. And what self-mask does is it just gets rid of all of the black zero value pixels from our analysis. So let's now add this layer to the map. So the layer we're adding is loss. In this case, let's just specify the palette as red for our loss pixels. And we can call this loss. I'll leave that for a moment for those who are copying to finish. And now let's press run. And we can see some really significant losses across the Amazon in particular since the year 2000. Much of these are actually conversions to agriculture. But all of these red pixels are pixels that used to be forests, but now are detected as degraded over time. And for just the sake of it, let's just quickly copy and paste our code to show where there might be forest gains as well. So we can just copy and paste lines 5 through 7. But this time, let's just replace lost with gain. Maybe let's change our palette to blue this time, and we can call this gain. It's good practice just to do both. We don't want to assume that just losses have occurred everywhere. And when we map that, I'll leave this up for those still copying. We can see that in many regions there are some, oh, sorry, we need to actually also replace this loss with gain. In some regions of the world, especially given reforestation in some kind of isolated hotspots in Southeast Asia, for instance, we do see some notable forest gains, but as a whole, you can see that forest change is still dominated by loss across the world. So this exercise, although it was simple and maybe not the most exciting, I think does a good job of just demonstrating the capacity of what you're able to do within a really short period of time at the global scale using Earth Engine. I'll stop briefly to ask if there are any questions before we move on to kind of a sample automatic way to do classification.
I don't see any questions right now, but please, if you have questions, put them in the Q&A tab at the bottom. Oh, there's something in the chat. It says, can we do prediction?
Yeah, so I'm assuming you're referring to things like forest loss prediction, and we absolutely can. So when we're predicting forest loss, it is a little bit more of a complicated method because we're trying to predict human behavior. But what we can do is run things like regressions over our data and understand the trajectory of where losses are most common over time. And then we can bring in some other data sets, like, for instance, where agricultural intensity has increased, where urbanization has been most prevalent. And by kind of comparing those with our past patterns of forest loss, then we're able to get a better understanding of hotspots that might be at greatest risk for future loss in the future.
Great. It looks like that's the only question we have right now. Thanks.
Okay, great. So I'll then move on to the next example then. Actually, I'll just quickly show you, if you're interested in saving this code, you can just press save. And then eventually you'll be able to just save it to your file folder. It seems like this is taking a moment, so I'll just move on. So let's open up another code.earthengine tab. And in this case, I decided to actually show you a bit of a new data set that has just come out that is really good for those who are pretty new to Earth Engine, but still want to be able to do some land cover classification. So everyone should search dynamic world. This was a data set that recently came out. And basically, it's a 10-meter resolution, meaning every pixel is 10 meters by 10 meters. That's really local scale, pretty much near real-time land use and land cover data set that basically uses the Sentinel-2 radar data as the underlying collection. And then automatically runs classifications in the back end for the probability that a particular pixel is one of several different land types. And as you can see from this band's area, you can see all of the different classes that they have. So this classification will help us identify areas of water, trees, grass, flooded vegetation, for instance, other classes like crops. And it's really good for kind of regional scale analyses. I will say that dynamic world is not meant to be very accurate at the hyperlocal scale. It's important that we use dynamic world just to get a general understanding of the land use, land cover dynamics in a particular region, but we still run our own classifications over a hyperlocal region. But for now, this is just kind of a good start. So we can import this. And let's just call this DW for dynamic world. So the first thing we're going to do is set a start date and an end date for our analysis. So this will help us kind of segment which years we're interested in looking at the land cover data for. So we can create a variable called start date, and maybe let's set this to 2015. And maybe we'll create our end date as 2022. So the first thing we want to do is load a Sentinel-2 image over our region of interest. So as I mentioned, Sentinel-2 is radar data. And here I'll show you kind of an alternative way to bring in a data set into your code editor if you didn't like the importing. Every one of these data sets that's already within Earth Engine has a unique ID. And so in this case, we can bring in Sentinel-2 by just saying var s2, and then we define this as an image collection. And here we just put this unique ID of Sentinel. So in this case, the unique ID is Copernicus. And then it's S2 _ harmonized. So a bit of a long ID, but this sometimes can make your code neater if you're able to just define it in line. So let's actually start to filter our data set. So here, in order to filter our data set for our beginning and our end time, we use a command called filter date. And our first parameter is going to be our start date, and our last is going to be our end date. The next thing we want to do is actually filter the extent of the image just to a particular point on the map, or rather any image that intersects that point. So for this example, you can try anywhere in the world. Non-cloudy regions tend to work the best for this. In this case, I like to use an example from North India, around Guwahati. I like to use this region because there is very frequent transitions of land and very frequent patterns of rivers shifting over time, especially around the Brahmaputra. So if we wanted to find a region of interest within Earth Engine, we can go to the top left of the screen, and you'll see these little icons here. And the easiest way is to just draw a rectangle or draw a point, for instance. In this case, I'll just draw a quick point. And we can just leave this named geometry, but you can also change the name if you're interested. So our next command, if we're only interested in getting our Sentinel imagery that intersects with that particular point, we can use the command filter bounds geometry. And the last just quick commands we'll do is try to filter out some clouds. This cloud filtering command is not going to be the best, but it's the best that we can do within just one line. So just bear with me because this is a long line. This is where we'll use our filter command. And within this, we'll just put the parameter ee.filter.less-than. And what this is going to let us do is just filter out all of the images that are covered by a less than, let's say, 35% of clouds. So it's only going to select the images that are not very cloudy. And to do this, there's a property called cloudy pixel percentage that is associated with every image within the Sentinel-2 collection. So it helps us filter out these cloudy images, and we can just set this at 35%. Okay, so let's actually try to just visualize this to make sure that we got any image. So let's just create a variable called s2 image. And we can create an ee.image, and then we take just the first image in our Sentinel-2 collection. And now let's add this to the map. So we can say map.addLayer, s2 image, and then the bands that we're interested in are bands 4, bands 3, and bands 2. Basically, we know that Sentinel has data for every part of the electromagnetic spectrum. And so we're only interested in looking at the 3 visual parts of the spectrum, the red band, the green band, and the blue band. And if you look up Sentinel-2 up here in this top box, then you'll see which band corresponds to what. And then here, I'll just put the min as 0 and the max as 3000. These are just good visualization parameters for this particular region. Don't worry about it too much just yet. And we can call this Sentinel-2 image. So let's run this quickly to see what we got. And we see that if we zoom out a little bit, this is a composite of the least cloudy images over this particular area intersecting with this point. So this is basically what this area looks like. Okay, so now that we have this general image of this area, you can see this is a particularly cloudy area actually, and so we weren't able to get rid of all of the clouds, but at least it's a start. Now what we need to do is actually get the image ID of our Sentinel-2 image. And what this is going to let us do is find the corresponding image in our dynamic worlds collection. As I mentioned, every Sentinel-2 image is matched with this dynamic world image that runs the land cover change classification over it. So we can just create a variable called image ID, and we take our S2 image and we get system index. This is just, again, getting the ID of the particular image that we looked at. And just for clarity, let's just print this quickly. And you see we get now the ID of this particular image that, again, we can use to link to our dynamic world data set. Okay, so now we want to do our actual matching with the dynamic world data set. So we can say find the matching dynamic world image. Let's create a variable called dynamic world. We know we already introduced our dynamic here. We called it DW. But now we want to select the image that corresponds to this index. So kind of like we used our filter up here to just select the least cloudy images, we're going to use our filter again and say filter in parentheses ee.filter dot equals system index, and then we'll set that to image ID. Again, what this is doing is taking our dynamic worlds data set, and we're only going to select the image with the system index property equal to the image ID that we already identified from our Sentinel image of interest. And this is going to give us just an image collection of just one image. So let's just isolate that image. So we can say dw image equals ce.image dynamic world dot first. Again, just picking out the first image. Now let's make sure we did this correctly. And now we see we have our dynamic world image, the image that corresponds with our underlying Sentinel data. We can see these properties and the bands associated with this particular classification. And to help this make a little bit more sense, let's actually add this to the map. So we know that each of these is just going to be a binary image, but the band that we're really interested in is this last label band. And this label band is going to be our classification band, where every pixel is going to be equal to its most likely class. So if we have a pixel over water, it will be equal to a value of 0 corresponding to water. So let's pick this out and say var classification equals dw image dot select label, because label is our band of interest. And now, since we have a fair number of visualization parameters that we want to use to visualize this image, let's just define a new variable called dwVisParams and set that equal to a whole bunch of colors. Just bear with me on this because they have these kind of nice preset colors for each one of the classes within our map. Blue, green, yellow, purple, red, orange, gray, black, and I think this one they also set equal to gray. And sorry, this should be open, closed, square brackets. And then finally, let's enclose all of this in curly brackets. And let's add a minimum of 0 and a max of 8. Sorry, just trying to find the small comma error somewhere. You needed to set this to a palette. Sorry, that took a moment. This should be the correct formatting of the visual parameters. And the last thing we want to do is actually add this to the map. So the layer that we're adding is our classification layer. We want to visualize it using the dwVisParams. And let's call this classified image. Now let's actually see if this worked. Okay, so lots of cloudy areas, but we can see generally some different classes are emerging here. We can see this did a really good job in blue of picking up the water, in green of the forest. I think the red is agricultural area. We'd have to go back and look at the exact classes for each individual color, but you can see this is a really good start for looking at classifications in our region of interest. And again, this is pretty useful when we're looking at, for instance, what the driver of deforestation was in a particular area, because, for example, if we wanted to know if an area was converted from forest to agriculture or forest to an urban area, for instance, then we could take 2 different Sentinel-2 images from 2 different points in time. And after that, we can complete our kind of matching up those Sentinel-2 images with our dynamic world images and see where these land use or land cover changes actually happened. So given that we just have 15 minutes left, I'll just show you a couple quick apps that really demonstrate kind of how we can take all of these Earth Engine analyses and make them interactive for users. So you can access these example apps by just opening up a new code.earthengine tab. And we can go all the way to the bottom here under examples. And this area is going to be excellent for kind of helping you get the basics for things like linear regression within Earth Engine. This code is actually really interesting because it helps us map regions where we've seen gains or losses in the intensity of lights that are shown from a particular pixel over time around the world, and is a kind of incredible visualization of electrification around the world. But the one I was most interested in was this user interface area. And these are all of these apps that you can create. So if we go to our Ocean Time Series Investigator, for instance, this is a really good example of kind of a really simple interface that even a new user of Earth Engine can create. So let's say you're interested in plotting changes in ocean temperature over time. You can create this pretty simple app where a user can click on a point of the map, and this chart will actually generate showing these changes on a month-by-month basis over our time period of interest. And you can also create kind of more advanced apps like this forest change app that is off of actually that Hansen data set that I started out with in the demo. And here you can kind of select between the different layers. But again, the goal of Earth Engine is actually not really to be the best coding platform out there, but really to be the best scientific analysis platform out there. So many people actually have some trouble kind of getting the coding syntax here. But the point isn't really to do it the most elegantly, unlike you might see in other coding platforms. The goal is just to create these real decision support tools that kind of bridge the gaps between the data that we're able to access from space and the needs of policymakers on the ground who, for instance, are interested in monitoring things like deforestation over time. And just one more that I'll quickly show you, this mobile-friendly UI. So a key use case of Earth Engine is actually allowing mobile users in low resource settings who wouldn't have access to laptops to actually be able to not only view data from Earth Engine, but also upload their own data. This is actually a pretty simple interface where you're just looking at this kind of global inland water data set. But the point here is that this isn't just restricted to those with laptops if you are interested in working in lower resource settings. And the last thing I'll just quickly show you as well is the developers page. It's just kind of a typical Google developers page, but here you can find the data catalog. And I really encourage you, if you're interested in Earth Engine, to spend some time going through and identifying different data sets that you think might be of interest to whatever your use case might be. And there is really extensive community documentation as well that both now includes many community uploaded data sets, where you're able to actually use data sets that are not already within the Google Earth Engine code editor up in this box here, but that different scientists around the world already created. And there's a pretty wide variety of online classes and tutorials that I encourage you to check out as well. So with that, with 10 minutes left, I will turn it over to questions.
Okay, I'm not seeing any in the Q&A, but if anyone has questions, please put those in the chat or in the Q&A. This is really cool, Liza. Thank you for sharing with us.
Sure, no worries. And please feel free to reach out if anyone has questions or has trouble starting up with the analyses.
Awesome. Okay. This will also be a recording. Let's see. We have one question. Is there any resource limitation in Code Engine?
There is, unfortunately. So when you are doing larger scale analyses, like for instance, running a random forest classification algorithm over a larger area, sometimes you will hit some resource limitations. It just depends on the algorithm. There's no kind of hard and fast rule. You can at times, if you're using the commercial version, I believe you can expand your limitations, but in general, what is kind of typical practice within Earth Engine is doing things like limiting the area of study. You can do things like exporting your image and then re-importing the image, actually, and so a single code isn't kind of redoing those computations over and over again. But in general, you'll just expect to hit those limitations for these larger scale areas or more computationally intensive algorithms.
Follow-up question. This is the same person. This is from Jason. Is the commercial Earth Engine paid through Google Cloud or separately?
I believe it's paid through Google Cloud, but you'd have to check me on that. I'm actually not, I just use it on the academic side, but I'd be happy to link you up with some resources for figuring that out.
Okay, we got one more question. It says, you just mentioned that upload data is also possible. Is there any benefit to upload data to the Earth Engine?
Yeah, so the main benefit to uploading data to Earth Engine would be that you're able to, I guess, first use all of the computing capacity to do things like image analysis within the cloud using Earth Engine, as opposed to within QGIS, where you're forced to kind of store all of the data and do all of the computations on your own. The other benefit would also be for public sharing. So a really common use case for me, for instance, is I might have some data that is already present within the Google Earth Engine catalog, like drought or rainfall data, for instance, but I want to upload, for instance, field data that I collected in forests. Then I can kind of intersperse the two of them within the same model and then create these publicly available apps that show it to the public. So Earth Engine you can think of as kind of like a vehicle for creating these decision support tools, even if you're not really using the data that they have in the catalog.
Okay, it looks like one more question from Paul. Can you post your dynamic world code sample?
Of course. Yeah, and I can link to what would be even better than mine would be, there's actually a whole kind of list of tutorials on dynamic world that the team put together. That's really excellent.
If you want to send that to me, I can send it as an email to all the participants.
Of course.
Awesome. Yeah, I'll send out a post-event email with that information and the other tutorials. Thank you so much, Liza. This was awesome. Sounds like that's all the questions. Oh, nope, there's another one from Jason. Is the data Creative Commons licensed by default?
I believe it is, but I always encourage you to check the conditions on each individual data set too that you're using. Often you do need to cite the papers, even if you don't need to cite the code that you use.
Awesome. Let's see. It looks like that's all. Awesome. Okay, we'll end this about 6 minutes early. Wait, I think, yep, you're just getting thanks in the chat now. This was really valuable and so great to see all the new tools you can use to visualize data.
Thanks so much.
Thank you so much. I'll reach out with an email with the recording and any links or tutorials that Liza sends me. Thanks, everyone. Have a good day.